Now let's take the dynamics from applications into account. We previously talked about line variations and load variations, and we might as well use the circuits we have investigated so far for applications that have AC at the input or at the output. So that means either the load resistor is not static, the power supply at the input to our converter is not a DC source, or we want the output voltage and output current to change according to the desired AC output. For those cases, one of the most widely used technology in power electronics is called pulse width modulation. So instead of keeping the duty cycle constant, we start to modulate it and have either a high duty cycle or a low duty cycle, and that signal is then called PWM, which stands for pulse width modulation. To generate such a signal, we feed a comparator, symbolized here, with the so-called carrier signal, very often a triangular signal, and compare it to a reference signal, which could be the control, the output of an error amplifier, or any other reference that we want the output of the converter to follow. The triangular signals are very often derived from an RC oscillator, or they are synchronized to any other clock in the circuit, which is provided by a crystal. There are numerous implementations of pulse width generation circuits. One that can do many things in one circuit is the one I'm showing you here, and this is called a hysteretic self-oscillating modulator. At its output, we have the PWM signal. Furthermore, we have the hysteretic window, which is simply a voltage division from the PWM signal done by those two resistors here. And we have a carrier signal on this node here generated by the RC division of the same pulse signal by those two components. Let's have a look at those signals as a function of time. Let's assume to start with that the pulse signal at the output at the time 0 just switched to the negative output of the comparator, which is very likely to be VSS. Through the resistive voltage division from those two resistors here towards ground, the window is simply a divided signal towards ground. And the carrier signal is an RC discharging of the capacitor down here. So it's an exponential function approaching the pulse signal at the end. But as soon as the non-inverting input of the comparator is higher than the inverting input of the comparator, the output of the comparator switches from its negative state to its high state, to its positive state. The window just simply follows this transition, and the capacitor now charges until the inputs of the comparator once more cross again, and the cycle starts all over again with the output of the comparator going negative. Now, if you would apply another signal out here, for example, a voltage source through another resistor, you could either help charging that capacitor or delay the charging of the capacitor by a negative current, and vice versa for the discharging of the capacitor. That would mean we start to modulate the duty cycle here. In this circuit, the modulation of the duty cycle would also have an influence on the period time t and would therefore also modulate the switching frequency.